Good morning, all of you. Welcome to Sri Jayendra Bank Zone. In the previous session, we have completed S block elements of alkali metals. Now we'll discuss alkaline earth metals in this session. This is also an important concept. So in this session, we are going to discuss about alkaline earth metals. So far, we have completed alkali earth metals, and based on these two topics, and finally, we'll do questions on alkali and alkaline earth metals in the coming sessions. So let us start now. S block elements, lecture 4. So, as I told you, in this lecture we'll discuss about elements of alkaline earth metals. Group, it is group 2. Group 1 we have done with some important points. Now we are going to discuss with group 2. So, alkaline earth metals is nothing but group 2 of the periodic table. So, it consisting of what are the elements? It consisting of beryllium, magnesium, calcium, strontium, barium, and radium. So these are all the alkaline earth metals. Beryllium differs from the rest of the elements like lithium, how it differs from the rest of the elements in the first group. The same way here, beryllium differs from the rest of the elements in the group and shows similarity in properties with aluminium. It has diagonal relationship with aluminium. So beryllium has diagonal relationship with aluminium like lithium has diagonal relationship with magnesium. Same way here, beryllium has diagonal relationship with aluminium. So what are the elements of this group? Beryllium, magnesium, calcium, strontium, barium, and radium. So these are called alkaline earth metals. Alkaline earth metals. Next continuation. So electronic configuration. The elements of second group have an outermost electron configuration NS2. You can just see here NS2. So for example, beryllium, it is 4s2. Magnesium, it is 5s2. Beryllium, magnesium, calcium, it is 6s2, and so on. So like this it will go. So beryllium, magnesium, sorry, it is beryllium is 2s2, very sorry. Here it is, beryllium is, I'm writing the atomic number. So beryllium is 2s2, magnesium is 3s2, calcium is 4s2, strontium, barium, and we have radium. So these are all the elements and so on. Like alkali metals, these elements also form predominantly ionic compounds. So all these except beryllium compounds, except few compounds of beryllium, except beryllium, all other compounds will form ionic compounds. Next continuation. So beryllium, helium 2s2, magnesium, neon 2s2, calcium, strontium, barium, and radium. So all these elements have the general outermost configuration NS2. So they have two electrons in the valence shell. So based on these completely filled electrons in the s orbital, definitely their ionization enthalpies are greater, much greater than first group metals, that is alkali metals. So the ionization enthalpy of these elements are much greater than alkali metals because of completely filled electrons in the outermost shell. So atomic and radii, ionic radii, the atomic and ionic radii of the alkaline earth metals is less than alkali metals, and down the group, the atomic radii and ionic radii increases from beryllium to radium due to increase in atomic number. So the atomic and atomic and ionic radii from beryllium to radium increases down the group due to the increase in size of the atom, whereas when compared to the atomic radius of alkali metals are slightly higher than alkaline earth metals. So the atomic radii and ionic radii of alkaline earth metals is less than that of alkali metals. Next, ionization enthalpy. The first ionization enthalpies of alkaline earth metals are higher. As I told you, it is very important point. They are very much high than that of alkali metals. This is due to the completely filled NS orbitals, because NS2 means it is completely filled NS orbitals and small size of alkaline earth metals. Also, the second ionization enthalpy of alkaline earth metals is lesser than that of alkali metals. Why? The second ionization enthalpy means removing second electron. The second ionization enthalpy of alkaline earth metals is lesser than that of alkali metals. Why? Because I will explain you the reason. So if you remove one electron from sodium ion, it becomes sodium ion. Next, second electron, if you want to remove, it should be removed from inert gas configuration, that is neon. Whereas in the case of magnesium, if we take first electron, If you move, it comes to inert gas configuration, that is Mg plus 2, it comes to neon. So automatically, so first electron is greater than second electron, but second electron you have to remove from sodium is, that is from inert gas configuration. That's why the second ionization enthalpy of alkaline earth metals is lesser than that of alkali metals, because for alkali metals the second electron is inert gas configuration, whereas for alkaline earth metals the second electron is not inert gas configuration. So that's why it is lesser. Very, very important point. Please note that point. Next, hydration enthalpy. The hydration enthalpies of alkaline earth metals are negative and it is higher than those of alkali metals. This comparison is very important because in the examination, they are not giving only one group, they'll compare with other groups also. So first group, second group is been compared, then 13th, 14th group is been compared, like that they'll give. So that's why the group comparisons is very, very important. So coming to hydration enthalpy, the hydration enthalpies of alkaline earth metals are negative and it is higher than that of alkali metals. The hydration enthalpy follows the order beryllium, magnesium, calcium, strontium, and barium. So as we go down the group, the hydration enthalpy decreases. The compounds of alkaline earth metals can form hydrated salts. They can form hydrated salts. Example, Glauber's salt, Epsom salt, like that. So what is Epsom salt? MgSO4.7H2O. MgSO4 Epsom salt is what? MgSO4, that is magnesium sulfate, hydrated magnesium sulfate dot 7H2O. So they can form hydrated salts. The alkali metal compounds do not form hydrated salts, but the compounds of alkaline earth metals can form hydrated salts. Very important point. Example, Glauber's salt, MgCl2.CH2O. It is also called as Glauber's salt. They'll ask the formulas also. And calcium chloride 6H2 also. It is also called as Glauber's salt. Next continuation. Physical properties of group 2 elements. Alkaline earth metals are silvery white metals and relatively harder than alkali metals. They are silvery white metals and are relatively harder than alkali metals. Beryllium and magnesium is grayish in color. Beryllium and magnesium is grayish in color. The alkaline earth metals have higher melting points and boiling points than alkali metals because they are much more stable than alkali metals. That's why they have high melting points and boiling points than alkali metals. So if they are given, based on this, they have given like this: sodium, potassium, magnesium, calcium, and the following in the increasing order of their boiling points. So the order of boiling points is what is the boiling point order? We can say, so as we go down the group, the boiling point increases or decreases. Boiling point increases. So we can say calcium greater than magnesium, greater than potassium, greater than sodium. Like this will be the concentration. So the alkaline earth metals have higher melting points and boiling points than earth metals. So these statements based questions you'll get, because from these statements only we have to write the orders. The metallic character of these metals increases from beryllium to barium, but they are less metallic when compared to alkali metals. So alkaline earth metals are less metallic when compared to alkali metals, but the metallic within this group, the metallic character of these metals increases from beryllium to barium. Calcium, strontium, and barium impart characteristic color to flames, while beryllium and magnesium does not. In alkali metals, all will give flame test, but in this group, beryllium and magnesium will not undergo flame test. Only calcium, strontium, and barium will impart characteristic color to flame test. Characteristic color to flame test. That point is very important. So this is because of strong binding of electrons in beryllium and magnesium, which prevents the excitation and de-excitation of electrons. Excitation and de-excitation of electrons. So the other metals which imparts color to the flame is calcium, it is brick red color, strontium, brick red color, strontium, it is crimson red, and barium, it is apple green. So calcium brick red, strontium crimson red, barium is apple green. So these are the colors introduced by this. Next continuation. Physical properties. Atomic number: beryllium, magnesium, calcium, strontium, barium, and radium. So what is the atomic number of beryllium? 4, 12, 20, 38, 56, and 88. Now atomic mass, it is 9, 24, 40, 87.62, 137, 206.03. Ionization energy. If you see the ionization energy, the first ionization energy in kilojoules is 899. Then, as moving from left to right, the ionization energy that is down the group it decreases. So ionization energy decreases down the group, and it is highest for beryllium. Second ionization energy is 1757, 1450, and that is also same. That is decreases down the group, and suddenly increase for radium takes place. These are of not that much importance. Next, hydration enthalpy, it is minus 2494, minus 1921, minus 1577 kilojoules per mole, minus 1443, minus 1305 kilojoules per mole. So, what do you understand by this? The hydration enthalpy decreases down the group. And metallic radius, it is 111, 160, 197, 215. So, down the group, the metallic character increases. Barium is more metallic than beryllium and so on. Next, ionic radius, 135 for barium, 118 for strontium. So, 100, 72, 31. So, down the group, ionic radius increases. Melting point also increases down the group. Melting point also increases down the group, exception for radium because it is radioactive. So 1516, 924, 1124, 1062, and 1002. So the melting point of magnesium and strontium. Magnesium and strontium. So magnesium is less. Why it is less? Because it forms hydrated formation. So melting point of magnesium is less when compared to R. So this point is very important. The melting point of magnesium and boiling point of magnesium is less when compared to all. So this order you have to write. Density is same. That is down the group. It increases. Next continuation. Chemical properties of alkaline earth metals. Alkaline earth metals combines with air and water. Powdered beryllium burns in air to form beryllium oxide. What they'll form? Beryllium oxide and beryllium nitride. Very, very important. So in the case of lithium oxide, lithium nitride, here also beryllium oxide and beryllium nitride. Magnesium readily burns to form magnesium oxide and magnesium nitride. So except beryllium and magnesium, all others will combine with only oxygen. So calcium, barium, and strontium are readily attacked by air to form respective oxide and nitride. So the general equations may be written as, so all the alkali metals, all the alkali earth metals readily combines with air, that is oxygen and nitrogen, to form the respective oxides and nitrides. This is called metal oxide and this is called metal nitride. Metal nitride. So metal nitrides and oxides respectively. So you can write the equations. This is a general form. For example, if I write for magnesium, 2 moles of magnesium combines with oxygen to form magnesium oxide from the air, and also 3 moles of magnesium combines with 1 mole of nitrogen to form Mg3 into magnesium nitride. So like this we have to take. In place of M, we can keep any alkaline earth metal. So note down these reactions, very, very important. Continuation now. Reaction with halogens. Alkaline earth metals react with halogens to form their respective halides of type Mx2. So direct combination with halogens and forms their respective halides of type Mx2. Example, MgCl2, beryllium fluoride, etc. Beryllium fluoride is prepared by thermal decomposition of ammonium beryllium fluoride. So NH4 taken to is BeF4. This is called diammonium beryllium tetrafluoride. Diammonium, two ammoniums are there. Beryllium tetrafluoride, four fluorines are there. So diammonium beryllium tetrafluoride on heating strongly forms ammonia gas, beryllium fluoride, and hydrogen fluoride gas. So beryllium fluoride is prepared from beryllium oxide. So beryllium oxide combines with carbon and beryllium chlorine gas to form beryllium chloride and carbon monoxide. These reactions are very, very important. Next. So what happens? All alkaline earth metals combine with halogens and forms their respective halides of type Mx2. Next continuation. Reaction with hydrogen. Alkaline earth metals except beryllium combine with, very, very important, except beryllium, combine directly with hydrogen to form respective hydrides. So here the M could be magnesium, calcium, strontium, and barium. No radium also because it is radioactive. So these are the elements from hydrates. Beryllium hydrate, it will not form directly, it is formed by indirect. So magnesium hydrate, calcium hydrate, strontium hydrate, and barium hydrate. So alkaline earth metals except beryllium combines directly with hydrogen to form their respective hydrates of type MH2. So beryllium hydride is prepared by reacting beryllium chloride with lithium aluminum hydride. This reaction is very important. So beryllium chloride with lithium aluminum hydride, it forms beryllium hydride, lithium chloride, aluminum chloride. Very, very important this reaction. Please note down. Definitely they'll ask question from this equation. So what is the final equation? How beryllium fluoride is formed? Beryllium fluoride is formed from beryllium chloride on reaction with lithium aluminum hydride. Beryllium chloride on reaction with lithium aluminum hydride to form beryllium hydride, lithium chloride, and aluminum chloride. Next continuation. Reaction with acids. Alkaline earth metals combine with acids, dilute acids to liberate hydrogen gas, just like alkali earth metals. So, like magnesium combines with sulfuric acid and forms one example I'm giving that. So, you can keep any other alkaline earth metal. It forms magnesium sulfate, MgSO4 plus hydrogen gas is liberated. Hydrogen gas is liberated. Next, like alkali earth metals acts as good reducing agents. They have large negative values of standard reduction potentials, but the reducing nature is less than that of alkali metals. Very, very important point. So, which is more reducing? Alkali earth metals are more reducing when compared to alkaline earth metals. Again, I repeat the statement. Alkali earth metals are more important and more reducing than alkaline earth metals because they last combining of these two elements only. Beryllium has less negative reduction potential than other alkaline earth metals. So beryllium has less negative reduction potential than other alkaline earth metals. So the weakest reducing agent is beryllium and the strongest reducing agent is lithium. So you can see the difference. Beryllium is the weakest reducing agent because of it has less negative reduction potential than other alkaline earth metals. Next continuation. Like alkali metals, they give deep blue color solution in liquid ammonia due to solvated electrons. Here, alkali earth metals dissolve in liquid ammonia to produce deep blue black. Here, the change is what? They will give blue black colored solutions due to the formation of ammoniated electrons. That is nothing but solvated ammoniated electrons. Solvated ammonia electrons. Due to the formation of solvated ammonia electrons, they form deep blue black color solution. Deep blue black color solution. You can see here. Here the M is called alkaline earth metal combines with X plus Y molecules of NH3 and forms MNH3, that is metallic ammonia complex plus solvated ammonia electrons. Solvated ammonia electrons also called as ammoniated electrons, which are responsible for the conductivity of the solution. And this is deep blue black colored solution. What is this called? Deep blue black colored solution, deep blue black, whereas in that case it observes red light and give only blue solution, and here it observes red light and give deep blue black solution. Deep blue black solution. Why it is happening, you can see here. This is due to next use of alkaline earth metals. Beryllium is used in making alloys. Copper beryllium alloy is used in high strength springs. Metallic beryllium is used for making windows of X-ray tubes. Magnesium forms many alloys. Magnesium aluminum alloy lighter and hard, which are used in aircraft and space applications. Some important alloys of magnesium are magnesium, electron, etc. Magnesium, electron, etc. So, what is the formula of electron? I'll just write here. Please note down because they'll ask in the examination. Electron alloy formula. Electron electron alloy. So electron is an alloy of magnesium, aluminum. So you can write here, I'll write here itself, electron, because they'll ask in examination, is an alloy of Aluminium, yttrium, aluminium, magnesium, mainly silver, etc. Aluminium, magnesium, silver is etc. So electron is an analog of aluminium and magnesium, silver, etc. So mainly it is consisting of aluminium and magnesium. Next, magnesium is used in flash powders inside the bombs and signals. Magnesium is used in flash powders inside the bombs and signals. Next, milk of magnesium. Magnesium hydroxide is used as an antacid. Whenever you get, that's why it is present in Rantac. Rantac is a medicine we'll be using for acidity. So to prevent acidity in our body, magnesium hydroxide is also called as milk of magnesia is used as antacid in medicine. Calcium is used in metallurgy to extract metals which cannot be reduced by carbon. Calcium is used in the extraction of metals which because it is highly electropositive. So to reduce certain metal from its salt solutions, we'll use calcium, which cannot be reduced by carbon. Radium salts are used in radiotherapy. Radium salts are used in radiotherapy. Next continuation. So these are the main uses of alkaline earth metals. Alkaline earth metals always forms divalent cations even though their second ionization enthalpies are almost double than their first ionization enthalpies. Explain. Very, very important question. Again, I repeat the question. Alkaline earth metals always form divalent cations even though their second ionization enthalpies are almost double than their first ionization enthalpies. Explained. So you can see here magnesium atomic number is how much? 12. So its configuration is 1s2, 2s2, 2p6, 3s2. So the number of electrons in the valence shell is 2 electrons. So if magnesium could remove, if magnesium can lose 2 electrons, magnesium loses two electrons, it becomes stable. So for attaining stability only it loses 2 electrons, it becomes stable like inert gas because 1 is to 2 is 2p6 is nothing but what? Neon. So it is a configuration of neon which is called inert gas. So if magnesium loses 2 electrons, it becomes stable like alkaline earth metals. So that's why the second ionization enthalpy is always double than the first one because first electron is the valence shell that is 3s1. Second electron automatically will be closer to nucleus. The second valence electron is closer to nucleus when compared to first valence electron. So automatically their second ionization enthalpies are almost double than their first ionization enthalpies because after losing 2 electrons they become stable. Next question. So next question we'll discuss now. So with this we'll continue with magnesium, alkaline earth metals. Now I'm sharing this. Compounds of alkaline earth metals. So general characteristics of oxides and hydroxides. After finishing this lecture, then the next lecture we'll discuss questions based on this. So alkaline earth metals readily burn in oxygen to form oxides of their metals, metallic oxides. So all alkaline earth metals readily burn in oxygen to form metallic oxide. All these oxides have a rock salt structure except for beryllium oxide. This point is very important. So the structure of these metallic oxides are having rock salt like structure except for beryllium oxide. Beryllium oxide is covalent in nature while all other oxides are ionic in nature. These oxides are thermally stable. All these oxides are basic except beryllium oxide. Since beryllium oxide is covalent, it is slightly acidic. So beryllium oxide is slightly acidic due to its covalent nature, whereas magnesium oxide is basic in nature. Magnesium oxide is what? Basic in nature due to its ionic compounds. Beryllium oxide is amphoteric, so we can say instead of acidic, we can say amphoteric. Which are the following are amphoteric oxides? They'll ask. So in that we have to check beryllium oxide. Beryllium oxide is amphoteric in nature due to its covalent character. These oxides dissolves in water to form hydroxides that are sparingly soluble. So it forms beryllium hydroxide. So all these oxides dissolve in water to form hydroxides that are sparingly soluble. So magnesium hydroxide, calcium hydroxide, beryllium hydroxide, and so on. Next, general characteristics of oxides and hydroxides. The basic character of these hydroxide, like magnesium hydroxide is basic, calcium hydroxide is basic, and barium hydroxide is also basic. Increases the basic character increases from magnesium to barium hydroxide. It means what? Which is more basic in nature, magnesium hydroxide is less basic when compared to barium hydroxide. That is based on basic character, less basic. The solubility and thermal stability also follows the same order. Solubility and thermal stability also follows the same order. That is, barium hydroxide is amphoteric in nature. Barium hydroxide on reaction with water, OH minus ions, it forms berylate ion. So this barium hydroxide on reaction with HCl and water, it forms BeOH taken 4 times Cl2. This reaction is important. Please note down in your classwork. This is nothing but beryllium hydroxide is amphoteric in nature. Next continuation. Alkaline earth metals form halides of type MX2. These halides are ionic in nature except for beryllium halides. Beryllium halides are covalent and have low polarity. These are soluble organic solvent except beryllium fluoride. Beryllium fluoride again it is ionic because fluorine is more electronegative. That's why beryllium fluoride is ionic in nature. So these are soluble in organic solvent except beryllium fluoride. Very, very important points. Just these slides are more than enough for writing questions, for answering questions, sorry. BeCl2 has a chain structure in solid state, so it will not form a single molecule, exist as polymer. One, two, three, just goes on. So many N molecules of beryllium chloride combined to form polyends of beryllium chloride. So it is not existing as single. So in Weber phase, beryllium exists, BeCl2 exists as dimer. Dimer means what? BeCl2 taken twice with a bridge chlorine bond. With a bridge chlorine bond. This is called bridge chlorine bond. So both bariums are combined together by means of chlorine. So it is called bridge bond. So this dissociates and exists as monomer at 1200 kelvins and above. So this dimer can change into monomer. Monomer means single molecule. At what temperature? 1200 kelvins. Halides of alkaline earth metals form hydrates on dissolving in water. So MgCl2.8H2O, calcium CaCl2.6H2O, barium Cl2.2H2O. Thus, it is evident that the extent of hydration decreases from magnesium chloride to barium chloride. These hydrated halides undergo dehydration upon heating, except fluorides as they have a violent reaction. So the hydrated halides undergo dehydration upon heating, except fluorides. Fluorides have violent reaction. That's why they are not hydrolyzed easily. Next continuation. Beryllium and magnesium halides hydrated salts undergo hydrolysis upon heating instead of dehydration. On heating, what happens? They undergo magnesium halides hydrated salts undergo hydrolysis upon heating instead of dehydration. The fluorides of alkaline earth metals have higher lattice energy than their fluorides. Thus, fluorides are less soluble than fluorides. So, fluorides of alkaline earth metals, that is, beryllium fluoride is less soluble when compared to magnesium fluoride, when compared to calcium fluoride, etc. So, these things you have to remember, otherwise, you cannot answer any question. Next, carbonates. Like how we have alkaline metal carbonates, we have alkaline earth metal carbonates. Alkaline earth metal carbonates are insoluble in water. First point. Their solubility decreases with the increase in atomic number. So these carbonates undergoes decomposition upon heating to give carbon dioxide metal oxide. So MCO3, this is magnesium carbonate or calcium carbonate or strontium or barium. On heating strongly will form magnesium oxide or calcium oxide or strontium oxide or barium oxide. Whatever the metal you take in form of carbonate, that metal oxide will form along with carbon dioxide. So beryllium carbonate is unstable and is kept in atmosphere of carbon dioxide. The thermal stability of these carbonates increases with the increase in cationic size. thermal stability of these carbonates. So which is more stable? MgCO3 is less stable than calcium carbonate, is less stable than strontium carbonate, less stable than barium carbonate, because as the thermal stability of these carbonates increases with increasing cationic size. Cationic size means barium plus 2, strontium plus 2, calcium plus 2, as well as magnesium plus 2. So out of all this, the size is bigger for barium carbonates. Next continuation. Sulfates. Sulfates of alkaline earth metals are white crystalline solids and are thermally stable. These sulfates have less solubility in water. The solubility decreases from calcium to barium. So barium sulfate, magnesium sulfate are readily soluble in water as their hydration energies that overcome their lattice energy. So the solubility decreases with the increase in atomic number. The solubility of sulfates decreases with the increase from atomic number. That is calcium to barium, the solubility decreases. Next continuation. Nitrates. All these elements form nitrates of the type MnO3 taken twice, because nitrate, magnesium nitrate, calcium nitrate, strontium nitrate, and so on. So these nitrates on heating strongly forms metallic oxides, nitrogen dioxide, and oxygen gas. Very, very important. Nitrogen dioxide and oxygen gas. These nitrates are thermally unstable and decomposed to give nitrogen dioxide and oxygen gas. So what are the elements we have? Beryllium, magnesium, all the elements of alkaline earth metals. These nitrates form hydrated salts, and the extent of hydration decreases with the increasing size of cation. So barium nitrate crystallizes out as anhydrous salt. So barium chloride or barium nitrate is barium nitrate crystallizes as anhydrous salts. So please note down. Next continuation. This topic will be like this only, very dry topic. You have to try to understand and apply the concept in the examination. Easily you can get success. Next, beryllium shows anomalous behavior. Like in the first group, we have lithium. Like that, in the second group, we have beryllium shows anomalous behavior compared to rest of the alkaline earth metals. This is due to the following factors. First one, small atomic size and ionic size, high ionization enthalpy, high electronegativity, valence shell electronic configuration. Due to the four reasons only, beryllium is anomalous when compared to other elements in the group, like in the case of lithium. Next, now we are going to discuss more points about beryllium. Beryllium has higher melting point and boiling point than other members of the family. Beryllium oxide is amphoteric in nature, very important. Beryllium oxide is amphoteric in nature, whereas the other oxides are basic in nature. Beryllium sulfate is soluble in water, while other sulfates are insoluble in water. Beryllium nitride is a non-volatile. Beryllium nitride is a volatile, whereas volatile means can which can cause effervescence. Effervescence. So beryllium nitride is volatile, whereas other alkaline earth metal nitrates are non-volatile. Very important, very much important point. But beryllium does not form peroxide like other alkaline earth metals do. So magnesium will form peroxide, calcium will form peroxide, strontium will form peroxide, and barium also will form peroxide with the formula Ba2O2. But beryllium, except beryllium, all other metals form their respective peroxides. Peroxide's formula is M2O2. Barium peroxide, MO2, sorry. MO2. These are formula of peroxides. MO2, not M2O2. It is only MO2. And the oxygen state of oxygen peroxide is -1. The oxygen state of oxygen peroxide is how much? It is equal to -1. Next continuation. The properties of beryllium and aluminum are very much comparable. This is similarity in properties that's known as diagonal relationship. As I already told you, beryllium exists as dimer, aluminum also exists as dimer. So that's why beryllium and aluminum are comparable with nothing but the concept is called diagonal relationship. So let us see what is the diagonal relationship of beryllium and nitrogen, aluminum. Very, very important. First point, beryllium and aluminum have same polarizing power. Second point, both form oxides that are amphoteric. Aluminum oxide, Al2O3 is amphoteric. Also, beryllium oxide is also amphoteric. Beryllium and aluminum carbides. This is very, very important. Please note down. This is used in the preparation of methane gas, an organic compound. So beryllium carbide on hydrolysis forms methane along with beryllium oxide, and aluminum carbide, that is Al4CA3, Al4C3 combines with water on hydrolysis forms methane gas. So preparation of methane from beryllium carbide and aluminum carbide. Most important. These reactions are very, very important. Please note down. So aluminum carbide Al4C3 on hydrolysis forms aluminum oxide along with methane gas. Methane gas is organic compound. Similarly, beryllium carbide Be2C on hydrolysis forms methane and beryllium oxide. Both form halides and hydrates that are polymeric. Chlorides of beryllium and aluminum have chlorine bridge structure in vapor phase. Beryllium and aluminum forms complexes and both have same value of electronegativity. So since most of the properties are comparable between beryllium and aluminum, they have diagonal relationship with each other. So due to the diagonal relationship only, most of the properties of beryllium and aluminum are comparable, such as the oxides of beryllium and aluminum are amphoteric. They are neither basic nor acidic. They are just amphoteric. The oxides of aluminum oxide and beryllium oxide are amphoteric in nature. Similarly, beryllium carbide and aluminum carbide on hydrolysis forms methane gas. This point is very important. Beryllium carbide and aluminum carbide on hydrolysis forms methane gas. Very, very important. And beryllium and aluminum form complexes. Both have same value of electronegativity. So these are the points based on which we have anomalous properties of beryllium takes place. Next continuation. Now compare the alkali metals and alkaline earth metals with respect to ionization enthalpy. Very, very important questions. Please note down this type of questions. So ionization enthalpy. First ionization enthalpy of alkali metals is less. First ionization enthalpy of alkali metals is less than first ionization enthalpy of alkaline earth metals. Alkaline earth metals. Alkaline earth metals. Similarly, second ionization enthalpy of alkaline earth metals. Second ionization enthalpy of alkali metals is greater than second ionization enthalpy of alkaline earth metals. Greater than second ionization enthalpy. It is the amount of energy required to remove the second electron, second valence electron, is called second ionization enthalpy. So second ionization enthalpy of alkaline earth metals is less. That is alkaline earth metals. This is very, very important. Please make a note in your classwork. So this is question number one answer. Compare the alkali and alkaline earth metals with respect to, first we have ionization enthalpies, basicity of oxides. Alkali metals are more basic. Alkali metal oxides are more basic than alkaline earth metals. Alkali metal oxides are more basic than alkaline metal oxides. Alkaline metal oxides. So the second property. And third one, solubility of hydroxide. The solubility increases. The solubility of hydroxides of alkali metals is less than alkaline earth metals because they can form hydrated salts, alkaline earth metals. So these are the points. Please note down. All these three questions are very important. So ionization enthalpy, alkali metal, first ionization enthalpy of alkali metals is less than first ionization enthalpy of alkaline earth metals, whereas second ionization enthalpy of alkali metals is greater than second ionization enthalpy of alkaline earth metals because Alkali has NS1 configuration and alkali earth metals has NS2. So first electron, after removing first electron, immediately it forms noble gas configuration. That's why second ionization enthalpy of alkali metals is greater than second ionization enthalpy of alkaline earth metals. Please make following difference. Next continuation. Compare the solubility and thermal stability of the following compounds of alkali metals with that of alkaline earth metals, nitrates and sulfates. So nitrates, alkali metal nitrates and alkaline earth metal nitrates, which is more soluble? Alkali metal nitrates, nitrates and sulfates we are given. So alkali metal nitrates with alkaline metal nitrates, alkaline metal nitrates comparison now we have to do. So please note down. So nitrates and carbonates or sulfates. I'll write the here answer. Nitrates and sulfates, nitrates, sulfates, and carbonates, all the three. I'll write here. Nitrates, comma, carbonates. Here carbonates are not given, but still I'm writing for your information. And sulfates of alkali metals are water soluble, are water soluble, and on moving down the group, the solubility increases. The solubility increases on moving down the group. The solubility increases on moving down the group. On moving down the group, the solubility increases on moving down the group. Alkaline earth metal nitrates are water soluble. On moving down the group, their solubility decreases. So if you compare the solubility of alkaline and alkaline earth metals, alkaline earth metal carbonates and sulfates have lower solubility than alkali metal carbonates. So alkaline earth metal carbonates, alkaline earth metal nitrates and sulfates, are less soluble than alkali metal nitrates and sulfates. Alkali metal nitrates and sulfates. So please note down alkali metal sulfates. Next, thermal stability. Alkali and alkali earth metal nitrates decompose on heating. So when compared to thermal stability of alkali and alkali earth metals, so the thermal stability of alkaline earth metals is more when compared to alkali metals. Thermal stability, you can see thermal stability of alkali earth metals is more when compared to thermal stability of alkali earth metals, that is less. So this is the answer. You can write this answer with explanation in your classwork. Just I have explained you, but you can see the NCERT textbook and you can write explanation clearly from your classwork so that you can write it better form. Next question. Since we do not have place, I have not written the reasoning. How would you explain the following observation? Beryllium oxide is almost insoluble, but barium sulfate is soluble in water due to high lattice enthalpy. High lattice enthalpy of beryllium oxide. It is less soluble. Barium oxide is soluble, barium sulfate is insoluble in water. So barium oxide has more hydration enthalpy. More hydration enthalpy than barium sulfate. Lithium iodide is more soluble than potassium iodide. This is iodide in ethanol. Lithium iodide hydration enthalpy is more. Lithium iodide more hydration enthalpy. More hydration enthalpy. That's it is solved in ethanol. So please note down. Anyway, these questions we have given ideas only for you, but however, you have to write the solution with the answers for these questions. You have to find for yourself only. In now with this, I'm ending this session. In the next session, we'll do more questions about so group two elements, that is alkaline earth metals. So with this, I'm ending this session. Thank you.